here. And I guess I should change this. Make me a student. I feel like I scrolled through our Moodle page, but maybe I forgot. Maybe I forgot. I've got our test dates posted. Test number 1. Test number 1 is when? 23rd. There. Thank you. 23rd of October, test number 1. Got some time, but it's also on 4 chapters. 1, 2, 3, 4, obviously. More of a sprinkling in chapter 4, but we'll talk about that when we get there. And then test 2 is on November 27th. Okay. You have to write it in class. There are no makeup tests. But if you miss it, I'll put the weight on the final. I'll do that for one of them. Whether your final exam is better or you miss it completely, those would be the same thing, but I'll do that for one of your tests, right? Shift it to the final. All right, good. So I made a note in our notes, about the test dates, just to be clear, but then also showing you the Moodle page. Okay. One thing as a quick little heads up here is I want you to notice the change of order here. The binomial is way more important that we cover. And then the rest of the distributions are kind of like whatever we can talk about is great. But the binomial is the most important. So I'm going to start with that and then go to 4.2. So 4.3, then 4.2, and then the others. So just make a note of that little switcheroo. So here, notice that. Oh, thank you.
You seem busy.
Awesome. Okay. Any questions about that? No. All right. Tests. They are going to be paper tests, although they could be online tests, but I got in trouble last year for doing it anyways. So they have to be paper tests. How weird is that? Anyways, I left you with this little application activity. We're just going to talk our way through it. We're not going to do it because there's a lot of work involved, but from last week, right, as kind of a review, I guess I should say, up here, I'll say review, right? We talked about conditional probabilities, and we leveled up to tree diagrams, right? We could use Bayes' theorem, which is an official version of the tree diagrams and using the tree diagrams, but conditional probabilities using tree diagrams, where a generic tree diagram might look something like this, right? I break it down, and you can have multiple branches, but for simplicity's sake, let's just talk about 2 branches, right? Where let's say A happened or A didn't happen, right? Those branches happen with some probability, P of A or P of not A, or the complement of A. Right? So I have my first set of events have to happen, and then I can decide the second set of events, which would be some event B, being super generic and vague here, but this is the general layout. So either B happens or it doesn't happen, either it happens or it doesn't happen, depending on what happened down these branches. There are scenarios where the probability of these is 0, right? For example, maybe if you went down, if A didn't happen, then B just can't happen, right? But what are these probabilities? These must be conditional probabilities, right? Conditional on A happening, right? And so down here, this is where it switches. The probability of B given that A happened. And then similarly, probability that B didn't happen given A happened. Probability of B given not A. The probability of not B given not A. And then what we said was, okay, if I need to find probabilities, the reason I prefer to use tree diagrams is it kind of lets me lay out the information. There's usually a lot of information to digest. So if you start kind of picking it apart into a tree diagram, putting it together in a tree, then it's easier to see what's going on. But also, when you're going down the branches, if you multiply the probabilities, right, that's the same as saying A and B, right? So then you're allowed to multiply. So then you have the probability of A times the probability of B given A, right? The conditional probability, which is the probability of A and B, right? So then down here, multiply down the branches, to find, to find the probability of A and B is the probability of A times the probability of B given A. Right, that conditional probability. This might be a nice time to remember that, okay, well, if these probabilities are not conditional on A, that can happen, they can be independent. Well, then what's the probability of B? It's just the probability of A or probability of B because it doesn't care what A is, right? So that's a special case, but you're safer by just assuming that it's a conditional probability and then arriving at, well, it's just the probability of B because they're independent, right? And so that's the special case, and this is always going to work, right? Kind of more, it looks bigger, but it's always going to work, so that's why it makes it safer. So then, multiplying down these branches, you would have the probability of A and not B, the probability of not A and B, and finally the probability of not A and not B. Woo! Usually we want to find things like, well, what's the probability of B, right? Well, the probability of B happened going down this first branch or going down the second branch, right? Whenever you're saying or, you're adding those probabilities. So you want the probability of A and B or the probability of not A and B, right? And so here to find the probability of B, which is pretty common, it's the probability of A and B or the probability of not A and B. That's why having these branches, if you can visualize all the ways that B happened, right, then you can just add those up. So that's the probability of A and B plus the probability of not A and B. What was the last check-in point? Well, at each level of these branches, the probabilities have to add to 1, right? If A happened or A didn't happen, is that the door or no? Now I've got the pseudonox. Pseudonox. I wonder if it's real. Right, either A happened or it didn't happen. The total probabilities have to add to 1, right? So here, how can I show that without bunging this up too much? Notice the probability of A plus the probability of not A have to equal 1. All right. Same with these guys. They have to add to 1. Because if A happened, then B can happen or it can't happen, but one of those two things has to occur. Right? And these have to add to 1. I'm lazy. Why? Because I should be writing the probability of B given not A plus the probability of not B given not A has to equal 1, but I don't want to write all that. So then I'm just saying they have to add to 1. And then finally, if I've listed all the possible combinations, well, then they also have to add to 1. There are some instances where if you've done some rounding, maybe they're not necessarily going to add to 1, but usually you just kind of adjust your rounding if there's something weird going on and make them add to 1. And so here, these probabilities have to add to 1. So just constant check-in points. That doesn't look like there. Making sure that you're on the right track. Okay. I'll start by just walking us through. I'll just hold your hand and walk through this application activity. We're not going to do it because the solutions are here, but I did kind of leave you on that note. And so this one's kind of ringing true, right? So a common epidemiological, I have to stumble through it, that's okay. Model for the spread of diseases is the SIR model, where the population is partitioned into 3 groups: susceptible, infected, and recovered. Fair enough. Covered all the possible outcomes, fit into one of those categories. This is a reasonable model for diseases like chickenpox, where a single infection usually provides immunity for or 2 subsequent infections. Sometimes these diseases can also be difficult to detect, of course. And then we're given all these probabilities, right? So imagine a population in the midst of an epidemic where 60% of the population is considered susceptible, 10% is infected, and 30% is recovered. Right? Split the population into those 3 categories. Okay. What would the first part of our tree look like? I'd have to have 3 branches at the top, right? Susceptible, infected, recovered, right? Okay, so it's already way bigger than what we were seeing before. So here, I'll just make a little note that my first branch is going to be SIR. Now, but wait, there's more. What infomercial is that? But wait, well, I guess it's all infomercials. But wait, there's more. Okay. If you order within the next 40 minutes, I'll throw in this, whatever, this conditional probability for free. The only test for the disease is accurate. Takes a little bit of time to think about what accurate means, right? If I'm susceptible, which means that I'm not infected and I'm not recovered, then accurate would mean that it shows a negative, right? Whereas if I'm infected, accurate would mean that it would show me a positive result, right? So you kind of have to take a step back and think about that. But it's accurate 95% of the time for susceptible individuals, 99% for infected individuals, but 65% for recovered individuals. What would accurate be for recovered? Accurate, it should be negative, right? A negative test would be accurate because they don't have it anymore, but they could still be showing a positive. Who knows? No, that's it. Right, and they've just got a little note about kind of thinking about what accurate means. So now we're going to draw a probability tree to reflect the information given above. That alone is a big task, right? And so, and then we want to know if the individual has tested positive, what's the probability that they're actually infected? Now, before I scroll down, I want to translate this final question here. It was all working up to this into probability notation. I want to find the probability that they're actually infected if the individual is tested positive. Right? And so if I have to translate this, this is the probability that they're infected given that they tested positive. That's not an easy formula to work with, right? So then we translate it into the probability of A and B over the probability of B, right? Read it like this and this over the probability of this because it had to happen, right? And so now, need more space, but the probability of infected, I'll put it on the next slide, I guess, given positive is, gonna need more there, is the probability of infected and positive, right? Those two together, divided by just the probability of testing positive. Which means, right, there were many ways of testing positive, right? If you are susceptible, you can test positive. If you're infected, you can test positive. If you're recovering, you can test positive, right? And so there are many ways, I should have been saying or in between there, right, to test positive. So this little guy, that's going to be the most work, right? So they put it on the half shell because it would take up too much room, and it's easier to read text like this, right? And if you want to draw your trees this way, that's totally fine. They're the same. I think we can all agree. So we've got SIR, susceptible, was 0.6. Remember, probabilities are always as a decimal, they're proportions, right? And so whenever you're doing math with probabilities, they have to be in proportions. That's important. Infected 0.1, recovered 0.3. And then, right, kind of keeping track of what accurate meant, right? Whether accurate means positive or negative, right? We can break it up and we said, okay, it was accurate 95% of the time for someone susceptible, which means accurate means it's negative, right? And well, the flip side of that would be a positive test, which is 5% of the time, or 0.05. Multiplying down these branches, right? You get the and probabilities. Now I get pretty lazy and I start to write just a little shorthand of the combination. So at the end of each of these, I just make a note to myself, this is S and P, or just SP, S not P. You can write negative if that helps, but I like to split it up into a yes/no situation if I can. This one is infected and positive, infected and not positive, recovered and positive, recovered and not positive. this way, it helps me see where all the P's are, right? Why do I need to know where all the P's are? My P's and Q's. I want to find the probability of testing positive, just in general, right? Well, this happened down here. It happened here, tested positive, here, tested positive, or here. Or, which means you're going to add those all up. Right. The top probability is not hard, right? Infected and positive, well, that's just one branch, right? That's this IP here. It has to be infected and positive, which has a probability of 0.099. Right? So that one's not hard, but then we divide by just all the positives. Right? They're not going to cancel. Why? Because I'm adding in the denominator and I would need to have a common multiple in order to be able to cancel, which is tempting, but it doesn't. Woo! It's been a while. Warmed up. Conditional probabilities. There. I'll call that how obnoxious. The end of our review. That was a rough and tumble review. There's a lot going on. And conditional probabilities, they're going to come back to haunt us, but I always get you to start by make a tree. So part A, make a tree diagram representing all these probabilities, right? If you can do that and you can't answer any of the questions, that's usually half the marks anyways, right? And then you can kind of go from there. But it also helps guide you. Okay, these are conditional probabilities. I'm going to need a tree diagram. All right. This is section 3.4, random variables. Random variables come up a lot in business especially, and you'll see why. It's kind of expected profits with the variability of the profits or the standard deviation of the profits usually. And so where do we start? Well, let's define what a random variable is. So a random variable is some outcome that depends on a random process or some random event, okay? In terms of notation, we use a capital X to denote the general event. For example, if I roll a die, so if X is rolling a die, then the possible individual outcomes are 1, 2, 3, 4, 5, 6, right? 5. So the values of a random variable are denoted with a lowercase letter, which we usually use lowercase x. Yeah. So here, just as a little example, if we let capital X, it's hard to tell, but my capital X, I don't put a little flare on it, but my lowercase x, I put a little flare on my lowercase x like this. So that's how you're able to tell my lowercase from my uppercase x's. It's pretty common because otherwise they look the same. If I let the capital X be this random process, I'll say rolling a die, then the outcomes are going to be 1, 2, 3, 4, 5, 6. I can roll one of those things. We can also find, so then we use this capital X just generically, and then I can say the probability that X is 1, right, has some probability. So how we use this is the probability that X is equal to 1 is 1 in 6. Or if you're lazy like me, sometimes I skip the x equals and I just go straight for the probability of 1. You can only do that if it's obvious what the event is, right? But if you are in a question where you're talking about rolling a die, then you don't have to specify, okay, the probability that x is 1 is this. You can just say the probability of 1 is 1/6, you know, if you want. So there are two types of random variables. There are discrete random variables that have discrete outcomes like 1, 2, 3, 4, 5, 6, etc. Okay, or some other examples like number of credit hours, or the difference in the number of credit hours this term versus last term, right? All these things that we can derive. We're going to focus on discrete random variables today. Okay. And then here, this is 3.4, and continuous random variables we'll introduce in 3.5, but we're only going to touch on it and then move on, and then come back to it a lot. Okay. So continuous, remember it's on some continuous scale, and so decimal values would make it continuous. Things like money are always continuous, heights, speeds, whatever, those are all continuous. But of course in business, money is the major one, right? And so that's our kind of go-to continuous variable. Okay. I guess any questions so far? So one of the two things that we're gonna have to be able to do after today is to find the expected value. Now, the expected value is just a fancy way of finding the mean, right? The expected value of x. So the expected value of x, capital X, because it's the random process, right? I roll a die, what am I expecting the outcome to be? Is the mean. And of course, the mean is the average, right? Kind of tracing it back, okay? And so when we find the expected value, it's going to be the weighted average of the possible outcomes. Okay? If we take a step back and dissect, if I told you, okay, I'm going to roll a die and they're equally likely to happen, right? We assume that. Okay. What am I expecting to see? What value would I expect to see, right? What's the average roll? Well, what would you do? Knowing only what we know so far, if we let x be rolling a die, the expected roll would yield what? 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, right? Oh. That's just the average of the rolls. This is where people get tripped up usually, because the expected value is usually not one of the options for the outcomes. Okay? So you kind of have to remove that notion. But here, what's this? This is the average or the mean roll. What is the average of this? I don't. 6 plus 4 is 10, 15, 20, 21 divided by 6 is Love it. I'll do this, 3.18.
Yeah, it's just a guess.
Oh, wow.
3.5.
3.5. Sold. I knew it wasn't going to be one of these things. So that narrows it down, I guess. But besides that, it wasn't very helpful. So for each roll, I would expect 3.5 over an infinite number of rolls, right? And that's why it can be something that's not one of the outcomes. Okay, so notice this is not an option for an outcome. But over many, many rolls, you would expect to see 3.5 on average. Yeah. If you had to map this formula back to this formula, oh, Emily, now you've done it. What are you assuming when you divide by 6? You're assuming that each one has a probability, has the same probability, right? Total probability has to be 1. You've got 6 things, so you smear it evenly across the 6 things, right? That's what you're assuming, okay? And so here, that's what I want to highlight here, is that this, and I'll add a page because I've got so much to say here. Notice when we divide by 6, we assume, that looks bad, but that's okay. Each outcome has the same probability. We also know that the total probability, right, has to be 1. So the total probability is 1. That's a fact. And in this case, we have 6 possible outcomes. 6 possible outcomes. Which tells me that the probability of X must be 1 in 6. Right? Doesn't matter what X is, if it's 1, 2, 3, 4, 5. Notice that that's a lowercase x. Right? So the probability of each X is just 1 over 6. I've spread it out evenly. So now if I map this back to this formula, I'm going to drop the mu here. It's true, obviously, but let's just drop it for simplicity's sake and say that, and maybe I'll just nab this here. Copy. Let's put her there. Then the expected value of X, which is the process, which is a capital X, is going to be the sum, right? The sum from I equals 1 to K, allowing for K possible outcomes, right? Is going to be the outcome itself, Xi, right? Times the probability of that outcome. We just declared that all these probabilities in this case are just 1 over 6. So that makes it easy. So in our example, right, rolling a die, we have the sum of, I could roll a 1 times the probability of 1 plus a 2 times the probability of rolling a 2 plus a 3 times the probability of rolling a 3 plus 4, I think you get it, probability of 4. 5 times the probability of drawing or rolling a 5, switching between cards and die, and oh my, ran out of space. We just decided that all these probabilities are the same, right? They're all 1/6, right? And so here, these are all 1/6. So I have 1 times 1/6, 2 times 1/6. Notice that I'm gonna have a common multiple of 1/6. I'm gonna write them all out, a little bit tedious, but just to show you, and then pull out the common multiple. And then, yeah, I'm checking with, and then we're gonna end up where we started, right? By adding them all up, dividing by 6, right? And so here, this becomes 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6. Should add these pre-baked. 1/6 and 6 times 1/6. It's so tempting, right, to simplify 6 times 1/6, but that's going to make the math harder, right? You can, but you'll set yourself up. So now I've got this common multiple of 1/6. Which means I can write, I'll do a large fraction here. 1/6, pull it outside. And then 1 plus 2 plus 3 plus 4 plus 5 plus 6. Which fractions, if I'm multiplying fractions, I'm allowed to just multiply across, right? 1 times that sum divided by 6. Whoo! 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. Back to where we started. Back where we started. But Emily, why would you waste my time with that? To show you that you already know it. Right? You already know how to do this. So now what would you have to do if I told you that the probability of a 1 is now 0.5, and then the rest are distributed evenly? What would you have to do? Well, now this changes, right? 1 is going to be times 0.5 or 1/2, whatever you want, right? You can use a fraction if you want, but 1 times 0.5, and then the remainder of 1 minus 0.5, maybe I should use 0.3 or something, right? Has to be spread out evenly amongst the rest, right? And so that's what we're going to deal with today. But in general, how we denote that is by taking, okay, you need to take the outcome times the probability of that outcome, and then add them all up. All right. How's this gonna, where can I use this? Well, game of cards, right? Game theory, all that fun stuff. Here, consider this. In a game of cards, you win $1 if you draw a heart, $5 if you draw an ace, including the ace of hearts. That's an option. $10 if you draw the king of spades, and nothing for any other card that you draw. Write the probability model for your winnings and calculate your expected winning. Why do we have to calculate the probability model? Because it lists the possible outcomes and the probabilities of those outcomes. It just makes it easier. You don't have to. Well, in this case you do because they're telling us to, but We don't need to, but we need that information, so it's nice to compile it in a table. So the probability model has X and the probability that X equals X. Right, and then we list all the possible outcomes up top and the probabilities of those outcomes below. Looks familiar, right? X equal, let's do this, X equals X, sure. All right. Little bit of a pickle. We can list the outcomes, right? But then we also need to be able to find the probabilities, right? In this case, not too bad, not too bad. And maybe I'll bump this down a little bit, give myself some more room here. What are the possible outcomes? I can draw a heart. That's one of the outcomes. And you can write it in words if you want. You can draw an ace, including the ace of hearts. Instead of specifying here, what am I going to do? Because what was one of the conditions of a probability distribution or a probability model? They have to be disjoint outcomes, right? So it doesn't really matter whether you put the ace of hearts with the aces, or sorry, with the hearts or with the aces, but because the winnings are different, what am I going to do? I'm going to put it with the aces. Okay, because I win more monies. Right? So I want to pull that out. So ace including ace of hearts and heart, which of course does not include, not including ace of hearts. Right, because they must be disjoint. All these outcomes must be disjoint or mutually exclusive if you prefer. But wait, there's more. Right, so now we've talked about the heart, the ace, and the ace of hearts, which is a special case, and then the king of spades, and then the final option is none of those things. You drew a card and it was none of those things. That can happen. King of spades. And some other thing. Right? You drew a card, it wasn't one of those things. Okay. We had to find the probability of all these things. Right. Then the probability of drawing a heart, but not including the ace of hearts. There are how many hearts? 13, yeah? 13, but then I take away the ace of hearts, leaving me with 12 out of 52 cards. Let me just, yeah. Okay. That's the probability of drawing a heart. That's not the ace of hearts. Okay. Now, what about the probability of drawing an ace, including the ace of hearts? Well, there are 4 aces in a deck of 52, and so I have 4 over 52. King of spades. That's only one possible draw out of 52. What are you going to do to find the probability of all the others? You're going to make sure that these all add to 1, yeah? So then you'll subtract 12 and 4 and 1, 17, who knows, I've got it, 35 out of 52. Right? You have to make sure that they add to 1. Right? This is going back to the probability model or distribution. All right, I think we called it a probability distribution earlier, but they're the same, confusingly, I guess. But just be aware of those, right? And there were 3 things that have to be true for a probability distribution or a probability model. I'll extend it there. First thing, they all have to be disjoint, all those possible outcomes. And all the probabilities have to be between 0 and 1, otherwise they're not probabilities. And they all have to add to 1 because it has to list all possible outcomes. That's all true. So far we're feeling pretty good. Okay. Drawing the king of spades, for example, is the outcome, right? But the monetary outcome is really what we're interested in, right? And so what I'm going to do is I'm going to map out, right, because I want to find my expected winning. And so if my winnings here, if X is the winnings, they're directly related to these outcomes, right? Now, if you wanted to, you could have written out just initially $1, $5, $10, or whatever it is, and then nothing, right? But it's easier to figure out the probabilities if you know what the outcomes are that you're looking for, right? So if we have the winnings for all these, well, we were told that if you draw a heart excluding the ace of hearts, you get $1 with the probability of 12 over 52. The ace, including ace of hearts, you get $5. The king of spades, you get $10. Everything else, you get nothing. Okay. So now you have some discrete outcome with the probabilities, and now you're able to find the expected winnings, right? So the expected winning or expected winnings. So then the expected winnings, oops, big S, I'll call it E of X. Is technically, right, you can write the summation notation first, right? And then introduce all the individual outcomes multiplied by their probabilities. But if you want to just skip to the good part, right, then you're taking this times this. Multiplication order doesn't matter. So if you want to multiply this by this, that's fine, right? Plus this times this, plus this times this, plus this times this. And so that's why it helps to have this probability distribution first, because then you can just multiply down, 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 add them up, and that's your expected value. But, oops, this is the sum from I equals 1, 1, 2, 3, 4 to 4 of xi times the probability that x equals xi. That's just snazzy. Showing off, really, the summation notation. Like I said, you can skip it if you want to. And if I copy this, put it on this next page. This is going to look like $1 times the probability of getting $1, 12 over 52, plus $5 times the probability of getting $5, 4 over 52, plus $10 times the probability of getting $10, 1 over 52, plus $0 times the probability of getting $0, 35 over 52. Bless you. This looks like a 6. I'm gonna clean that up. If you had to tackle this without the formulas, this is where you would end up, right? You'd say, okay, I can figure out the probability of drawing an ace. That gets me $5, right? But this is just a more structured way of solving it. Okay. And pre-baked. Let's see, this becomes, and because it's so small, I'm gonna copy it. This becomes 12 over 52 plus 20 over 52. I guess I could have done that myself. 10 over 52 plus 0 over 52 technically. Sure. Mostly because I also teach math, obviously. Adding fractions, you have to have a common denominator. But now, here we are, 12 plus 20 plus 10 plus 0 puts me at 42 over 52. And 42 over 50, 522. Nope, try again. I get 0.80769230077. But because it's money always rounds to 2 decimal places, right? And so $0.81. Careful you don't write something silly like 0.81 cents. That's really little. 81 cents isn't that good either. But if you're playing for free, that's pretty good. What if I told you it's going to cost you $1 to play? Well, it depends on if you like to gamble, I guess. But your expected payout is 81 cents. So in theory, you shouldn't play the game unless it costs less than 81 cents. That's never the case. It just doesn't work that way. But this is your expected winnings. Notice that again, that's not one of the options, right? But your expectation is 81 cents. Your only options are $1, $5, $10, or $0, right? So just keep that in mind, that the expectation is in the long run, right? If you do this many times. Okay, good. We can visualize this, right, with the probabilities, but this just emphasizes that, well, the highest probability of something happening is none of those things, right? And then this is what it looks like. I prefer the table, actually. This is just a visualization of the table, right? 0, 1, 2, 3, 4, 5, all the possible outcomes. I don't know why actually. Oh, dollars. Here, this is the payout. Nothing in between. And this is just a visualization of the table. Oops. All right, don't let it throw you. All right, good. That's a valuable skill. What about the variability, right? What about the fluctuations in these earnings? How are we going to find that? It's a little bit trickier, but we can find the variability of a random variable just by giving that probability distribution. You can find the mean or the expected value and the variance of X, or the standard deviation of X if you prefer, which I do prefer. But sigma squared is the variance, which again, we're ignoring these Greek letters for just a little while longer, but it's good to see them. It's good to see them. So sigma squared here is the variance of X, and we can get there intuitively, but it's going to take a little bit more work. Okay. Let's see. But it's going to be the distance of each payout in the previous example, or the distance of each outcome from the expected outcome, right? So what's the distance between the expected outcome and each of those outcomes? Then we square it and then multiply it by the probability of each of those things. But this probability is the same as the probabilities earlier. So once you have them, you can recycle them, and you should. And then, of course, the standard deviation is the square root of the variance, which means that usually we find the variance first, take the square root, and then we have the standard deviation. So a little bit more work. Business
like
accreditation.
Yeah, like in respect to like running your own business, like I'm just struggling to see the application.
I guess if you have, so often you'll have different profit functions, and those would give you the different probabilities, I guess. But
because I know this is just
our
like a beginning
worlds are,
but like I'm just struggling to see like where exactly this comes into play.
let's see, there was let's see if this one, oh, the homework one, that's not the one I was thinking of. Yeah, so again, not applicable.
It's okay.
But usually, well, yeah, we have to do it for accreditation. That's a big one for me, right? Have to cross my T's and stuff. But I do know that it's only business who forces you to do it. So there must be a reason.
Right.
Besides that, I got nothing.
Okay, that's cool. That's fair.
Is it cool? I don't know. I should find a reason. I'll make that my homework. All right. So if we use the formula from before, then we can use these winnings, right? The payouts or the outcomes, right? We're using the numerical ones because we can't do math with aces and hearts and whatever, right? But they are attached to some number. And we had the probabilities, and we already found the X times the probability of X, and we added them up to find the expected value of X. That's all gravy. Now we're moving on to the variance. All right, so this portion is for finding the variance. If we break it up, this formula here, we need the sum of each of the outcomes minus the mean and then square it. So I like to break it up into multiple columns, but it takes up a lot of space. So here they've done it in one. Take the outcome, subtract the mean, right? 1 minus 0.81, 5 minus 0.81, 10 minus 0.81, 0 minus 0.81, sorry. Scroll up. Then square it, right? That's important. Otherwise, you'll have negatives and they'll all add to 0 and it makes a mess. Okay. So we square those and then we have the first component, and this component is this chunk, which we then multiply by the probabilities from before. All right. So then the probability that we have from before times the column that we just found, and I'm gonna skip to the meat and potatoes here. The variance of x, you have to add these values up, but I'm just gonna tell you is probably roughly 3.4246. Which means that the standard deviation of x is the square root of 3.4246, which is from here 1.85. But there's probably rounding, so if you're using, Excel or whatever, they'd get better values probably. Nice. So usually I'm going to ask for the standard deviation. What's one of the problems? Oh, I need to introduce one thing first, maybe two things. Tried to segue too early. What if I have a combination of random variables? So I can have two random variables. I can flip a coin, I can roll a die, I can draw a card, right? I can have as many random variables as I want, right? And so what we would have is some linear combination of random variables, right? A times X and B times Y, right? X happened A times, Y happened B times. How the expectation behaves is exactly how you want it to. And I say that because the variance doesn't, okay? And so here, if I wanted to distribute the expectation onto this linear combination, then I just bump the A outside and the expectation latches onto the random variable. The expectation of a constant is just the constant. So technically you're putting it on the A and the B as well, but they just return themselves. And so it becomes redundant, but this becomes A times the expected value of X plus B times the expected value of Y, right? So here the expectation distributes onto random variables. So they've got this scenario. If on average you take 10 minutes for each statistics homework problem and 15 minutes, hey, for each chemistry homework problem, I guess maybe that's better for me. If this week you have 5 stats problems and 4 chem homework problems assigned, what's the total time you expect to spend on statistics and physics homework? Physics? Hexagons? Wouldn't that be a curveball? And biology homework for the week. Wow. Okay. Yeah, everything else matches. Okay, good. So now, right, you've got, what are we given? We're given the expected time spent on each stats question and the expected time spent on each chemistry question. So here we're given that I'm hesitating because I should really define X and Y first. let X be stats questions and Y be chemistry questions. Fine. Let X be, whoops, really mess you up, statistics questions. And Y be chemistry questions. If you wanted to, you could use S and C, right? Kind of more obvious choices, but I want to map it back to that general linear formula. So the expected value of X, this is where I was gonna jump in, given the expectation, so the expected time spent on a statistic question is 10 minutes. And the expected value of Y was 15 minutes. Now, if you have 5X and 4Y, right? Then we want to find the expected value of 5X plus 4Y, knowing that the expectation distributes, right? Then I can say, well, that's 5 times the expected value of X plus 4 times the expected value of Y, which I have. That does look like sex, but 5 times 10 plus 4 times 15. All right. 50 plus 60 is 110. Sold. You would expect to spend 110 minutes on your homework, understanding that there's variability, right? Understanding that some take longer, some are shorter, but on average, which is the expectation, right? You would spend 110 minutes. Here's where, and let me see, oh boy. Chop, chop, Emily, chop, chop. What if I want to find the variance of a linear combination, right? Again, knowing some take longer, some are shorter. The variability of a linear combination is going to be this. So the variability of A times X plus B times Y, that's the same format as before. But what happens is when I pull that A or kind of distribute that variance, I have to square the coefficient. It's just something to remember. It's not something we're going to look into. Okay. And so here, so this becomes A squared times the variance of X plus B squared times the variance of Y. Of course, once you have this overall variance, you can take the square root and that's the standard deviation, right? And so notice the coefficients square, and this is gonna probably trip you up because it always does. The coefficients square when we distribute the variance. Okay. There is a note, but we're definitely not doing that. If the random variables are not independent, then it gets a little bit more complicated and we're not gonna deal with that. But that can happen, but we're just not gonna deal with it. What if I have the standard deviation? So we're given the standard deviation of the time it takes to do these problems. For statistics is 1.5 minutes and 2 minutes for a chemistry problem. What's the standard deviation of the time you expect to spend? Well, this is the same as before, right? So again, I'm gonna let X be statistics and Y be chemistry. we were told that the standard deviation of X, whoops, is 1.5. And the standard deviation of Y is 2. We have to do a little bit of work because our formulas involve the variance, but the variance is the standard deviation squared. So, wait, trash the place. The variance of X then is going to be 1.5 squared, and the variance of Y is going to be 2 squared. 1.5 squared, is it? Thank you. And 4. Same deal, right? But now I want to find first, I ultimately want to find the standard deviation, the time spent, but my gateway to that is the variance. And so I want to find the variance of 5x plus 4y's, remembering that when I distribute that variance onto, the variance of 5, if you think about it this way, is just 5, but when I distribute the variance, or it's 0, sorry, because it's one value, it doesn't move around. When I distribute the variance, then I have to square the coefficient, and that's just a fact. We roll over there. 5 squared times the variance of X plus 4 squared times the variance of Y. 25 times 2.25, yeah. 56.25 plus, right, 5, yeah. 4 squared is 16 times 4 is 64 plus 56.25. I get 120.25. But it asks for the standard deviation. Usually this is where I get messages, I found the variance, it's saying it's wrong. Well, did you square it or square root it? The standard deviation of 5x plus 4y is the square root of 120.25. And do I have it? Oh. How come my answer is different than their answer? Oh, dang. That's okay. I'm actually gonna leave it. Mostly because I'm running out of time. I feel like it should be the same. 586-ish. In my pre-baked notes, well, there's also a typo here. 27.25. I disagree. Temporarily disagree. I want you to do it this way. But I will look into that. Okay. Let me just see here. Oh yeah, okay. A casino game costs $5 to play. So you haven't even started, costs you $5, which is more realistic, right? If you draw first a red card, then you get to draw a second card. If the second card is the ace of hearts, you win $500. If not, you don't win anything. That is, you lose your $5. What's your expected profits or losses from playing this game? So the profit or the loss, the winnings minus the cost, of course. And we want to find the expected profit, okay? And so one thing that I will clarify here, and I will just confirm, is it's without replacement. Okay, and so that should be here somewhere. Without replacement. How sad are you if you draw the ace of hearts on your first draw? Oh, without replacement, the probability of you drawing it on the second draw is 0. You've already lost. All right. So first thing we're going to do is we're going to say, okay, we want to find our expected profits, which means that our outcomes are the profits, right? So I can have a profit of 500 minus $5, right? If I win 500, I have to take away the cost of $5. Let's go with $4.95. Can have a profit of $495, or I can have a profit of $0. Okay. What's the probability that x equals 495? Which is really saying, what's the probability of first drawing, right? First you draw a red card, then you draw the ace of hearts. Yeah. So that's a conditional probability, right? And so this is going to be my first card. The probability of drawing a red card, let's start there, is 26 out of 52. But what did we just establish? Little sneaky. We're hooped if we draw the ace of hearts. So we really only have 25 out of 52 cards that are going to yield a profit of 495. But then I need my last card. There's only one choice for my second card, but now I only have 51 cards to draw from. And then all the others, so this, and maybe I'll scoot this over a little bit. So this puts me at a probability of 0.0094. $0 has a probability of 1 minus 0.0094. I don't need to work it out or anything. You can just subtract from 1, which is 0.9906. The expected profit, which is X. So here I'll clarify, X is the profit. The expected value of X is 495 times the probability 0.0094 plus 0 times 0.9906. And we get, stealing from here, and I hope I took the right one. Negative means a loss. So a loss of 30 cents. I think it's the last slide. A fair game is when the expected cost is the same as the payout, but that never happens. Ta-da. Any questions? Yeah.
Can you scroll back on the slide?
Yes. You didn't want to look at the Vegas picture?
How did we end up with a negative coming out of this? If we're adding a positive.
Oh, that's a good question. Yeah, where did I get that? Oh, haha. Sorry. I'll do it in red because I really screwed up. You had to pay $5. You're down $5. There. And remember, no labs this week, so if you have a lab today, you're free. I'll see you next Wednesday. Thank you for catching that.
Thank you.
See ya. All right. Oh, yes, awesome. Thanks, guys. Stop this.